morning, everybody. We're going to start the webinar in 2 minutes. See you soon. Good morning, everybody. Thank you so much for joining us today for our 5th webinar of the CLT Toolbox webinar series. Today, we're going to be covering the CLT design for a residential mass timber building. If I haven't met you before, I'm Adam. I'm the CEO of CLT Toolbox. I'm a structural engineer and really excited to be co-hosting today with Marko, our product manager, presenting on today's webinar. So as a bit of an agenda for today, we'll be doing an introduction, we'll be doing some housekeeping, we'll look at some of our latest releases, and then following that, we'll go to the worked example with some really exciting new calculators that are happening on the platform. So on this community forum that we've got, this webinar infrastructure, you see you've got a few buttons on the bottom here. So on the left-hand side, you've got a webinar chat. Feel free to introduce yourself, say g'day, and speak amongst the attendees as much as you like there. Or you can also ask questions in the question mark box there, and then Marko or myself will get to the questions at the very end. So right now, because we've got 5 webinars, we have started creating a bit of a bank of pre-recorded webinars. So right now we're at about 5 and doing a monthly right now. We have also been putting individual calculator tutorials up on YouTube as well. So they help you with education on specific calculators in the app. All right, so since we last spoke about a month ago, we have done a couple of releases. So if you're new to CLT Toolbox, what we do is we build enabling timber engineering software to make it as easy as possible to specify timber building products, whether it be CLT, glue lamps, screws, or brackets. And as you can see here, one of the releases we did recently was a brackets module with additional connection details. So with this, a new bracket module with the product suppliers Eurotech and Sigga, we released a shear reinforcement calculator. We released 2 new connection details with it, which is a slab to wall screw connection detail. That will be covered in today's webinar alongside the bracket modules. We've also released 2 in-demand features. One was duplicate projects, and another one was a little bit messy in our screw ordering. So as we keep building and building the software, you'll see improvements like this continuing. And really excitingly, and most of the focus of today's webinar is an upcoming release, and this is going to be on Friday. We have new member calculators, one being a stud design calculator. So our first light frame calculator on the platform. We've also got a CLT floor penetration coming on, which we may do a sneak peek today. We've also got a major update of the shear wall calculator. There's a few user experience things and how we've added the bending moment and the wall connection transfer mechanisms. Also the CLT beam, we've done a major upgrade, and also improvements in PDF printing. So before we get to Marko, it's always great to do a big thank you to our partners. We wouldn't exist if it wasn't for all of our partners here. So everyone on the screen here, if you go to the CLT Toolbox platform, you can design with their products for free one way or another. And as you go on, you'll see the actual products and the categories expand as we do more and more releases. So I think, there's not many platforms like ours, but without doubt, we are probably the biggest platform in terms of having a supermarket of choice for engineers when designing products in the timber ecosystem. And we're excited to make more announcements soon. So we are building really fast and accelerating some of the partnerships that we're getting on the platform. And for those in Europe who's making the journey to Australia next week, so the World Conference on Timber Engineering, it's really exciting. So we're going to be hosting the welcome drink. So really recommend if anyone here or anyone of your team is actually coming to Australia for the conference, I think there's going to be hundreds and hundreds of presentations. So it's a good opportunity to geek out on timber engineering and get excited by all of that. So come say g'day and have a drink with myself, Ringo and Corey, who will be making the trip. So with that said, right now, we're really excited to present today's webinar topic. So Marko, I'll pass it over to you, mate.
Thank you, Adam. So hi, everyone. Let me just share my presentation. Okay, so thanks everyone for coming. I'm Marko. I'm product manager here at CLT Toolbox, and I'll be your host for today's presentation. So we're going to talk about the CLT design for residential mass timber building. In today's episode, we'll cover CLT wall design, and we'll talk about eccentricities, and then CLT wall design in case of fire, CLT shear walls with pointing out the different methods and design options. Then we'll check a newly released bracket design calculator, as Adam mentioned, and CLT compression perpendicular to the grain checks, together with floor to wall connection calculators. So for today's example, we'll have a residential 4-story mass timber building with L-shaped base. The building we are talking about is located in Stockholm, with overall dimension of 15 times 20 meters and a story height of 4 meters, or a total height of 20 meters. Floors are made from a single 2-span or a 3-span CLT slab, spanning in both X and Y directions. CLT slabs are supported by CLT walls and glue lamp beams. For the lateral support system, we have a series of CLT shear walls predicted in both X and Y directions. So based on the preliminary analysis, we have already designed CLT floors, GLT beams, and columns. On the floor plan on the right, you can see all the positions of floors, walls, and beams and columns. And for CLT floors, we have 5 layers, 140 millimeter panels from Sodra. For beams, we need 200 by 580 millimeters GL24C, and for columns, 260 by 260 GL24H. Since we already shown how some of these calculators are working in the previous webinar episode, now we'll focus on CLT walls. So going straight to CLT wall design, so we'll look at the beginning at the CLT wall in axis 5. So we have following loads on this wall from the supported CLT slab. We have a tributary area of 2 meters. So the reactions from the supported slab are dead loads are 5.4 kilonewton per meter, and imposed load is 5 kilonewton per meter. Laterally, out of plane loads from wind are acting on this wall with the intensity of 1 kilonewton per square meter. And additionally, we have vertical forces from above levels. So we have dead loads of 21.6 kilonewton per meter, or totally we'll have 27 kilonewton per meter. And imposed loads, we have reactions from above floors of 12 kilonewton per meter, or totally 17 kilonewton per meter, and snow load reactions from the roof of 4 kilonewton per meter. Before we go to actual design of CLT wall calculator, we'll talk about briefly about different types of CLT wall framing and their eccentricities. So in general, CLT walls could be with platform or balloon type framing, as shown here. In balloon type, presented on the right, CLT structures So the CLT walls extend continuously through the full length of the building, with the floor panels that are attached or suspended at each story. In our case, we're looking at the platform type system, so as shown in the middle, where the floor platform of each story services as a base for erecting the CLT walls of the next story. And as a result, the height of CLT walls corresponds to the story height. And also important to point out that CLT walls transfer gravity load at each level from the story above to the CLT floor panels below. If we want to point out something about the eccentricities and the methods that are implemented in our app, so wall eccentricities in general are derived from firstly geometric imperfections, which refer to deviations and inconsistencies arising from factors such as manufacturer tolerances, material variability, and construction's inaccuracies. Then we have actually load eccentricity from above, in case of that loads from above are not centric. Then out of plane deflections, so from out of plane wind forces, for instance. Then there's also neutral axis shift due to section loss from fire or unsymmetrical layups or other factors. And all of these four eccentricities represents the first order eccentricities, while the last one, or the second order eccentricity, and also referred as the P delta effect, occurs when an eccentric axial force from self-weight or from applied load in combination with axial or horizontal loads generates a bending moment and additional displacement. These effects can also develop to do the charring of the fire exposed surfaces as well. So that being said, we'll show you what some of the methods we have available in the app. So in CLT Toolbox, there are 4 available methods for addressing CLT wall eccentricities. There's manual input, where user can input only a single total eccentricity together with a loaded eccentricity from above. Canadian CSI method. So in this method, user can define the actual load eccentricity from above. Geometric imperfections, first and second order eccentricities, are determined according to the standard. For the US CLT handbook method, user can define both actual load eccentricity from above, but also geometric imperfection is something on the user input. But while the first and the second order eccentricities are determined according to as described in the standard. For the revised Euro code, similar to Canadian code, user can define only actual load eccentricity from loads from above, while geometric imperfection, first and second order eccentricities, are determined per code. So that being said, we can jump to the app and show how these calculations and methods actually are working. So if we go to the app, we'll start with CLT Wall Design as we described. So let's create a new calculator. I'll add to our enterprise profile. So let's go webinar episode 5 and start with CLT Wall. So as we have a calculation run, so we'll select the appropriate supplier. So in this case, we'll go with the Sodra layups. We can start with 5 layers, 130 millimeters. As you're probably aware, everything in this case works dynamically. We have also a preview of some of the verification checks performed. So we will add Sweden National Annex as well, and we'll continue to the analysis part. So here we'll proceed with extended gamma. We don't have any intermediate restraint. We have a floor level of 4 meters and framing type platform, as we mentioned. Concerning loads, we'll check in all loads acting on this wall. We'll proceed with the fault load combination. For the category, for imposed load category, we can go with the residential area. A snow load can be between 2 and 3 kilonewton, and we'll take both equations for the design. Self-weight can be considered, and from the actual load from above, we'll type in 27 for the dead loads, 17 for the live. For the wind, we'll have from gravity will not include, and for the snow, we'll have the 4. For the lateral load from the wind, we'll have 1 kilonewton per square meter. If we go to the eccentricity part, so this is the part we briefly touched before. So we have these 4 available methods, starting from manual input, a Canadian, USA method, or revised Eurocode. So additional inputs are also included into educational part. So as for the other parts, there's a way that you can find some more information on what are the differences between these eccentricities. And basically some of the workflow around which type of eccentricities is included and how it's calculated in. So for this case, we can go with a new Eurocode method. So detailed part is and step-by-step are also shown in the eccentricity part, which we'll cover in a few seconds. So if we have also the cases can be maintained as 1.1. In terms of the preview of the results, we can see that in this case we have all the checks performed, and the utilization is around 66-67% governing with the sliderness. Concerning we'll have the fire design, we won't optimize this section anymore, even though we can probably go with even lower cross section, but we'll briefly go through the results and proceed to the fire design afterwards. So in terms of the stiffness calculation, so as in the previous calculation, everything is displayed here for the extended gamma method. Annexes, so all the information related to Swedish National Annex are included in this part. For those who weren't at the previous webinars, all of our calculations work in a similar architecture that we present all the data and step-by-step calculations. For the loading code, so depending on all, because we have all the load type included, we have a preview of loads, also serviceability and ultimate limit state loads. All for the eccentricity part. So as I mentioned, this will refer only for the new Eurocode method. So we have all the eccentricities stated here. So this is related to the first order eccentricities, equivalent meant out of plane wind loading deflection is also included in this case. In terms of the analysis, so based on the loads and load combination that are included, we have information about actual loads, bending actions, and moment due to lateral pressure as well. If we scroll down, we'll also have how the total design moment is included in this case, and we can change practically and see what is happening with both actual loads but also bending in terms of each load combination accordingly. The last part of our checks, including the design codes or sliderness checks. So within that, we have in both information for this step-by-step process. So concerning the actual design, bending capacity, and combined stress. So that being said, we can jump back to the presentation part and just overview some of the results we have. So we know that 5 layers, 130 millimeters from Sodra is something that we can go further, and we have governing sliderness. So next step, we'll have the same panel, same inputs, and we'll just cross-check with fire design. So in this case, we'll try to have a 60 millimeters fire protection requirement with the protection and exposure just from one side. So this is a external wall. So it's something that is usual to have situations like this. So it's also important to mention that the additional first and second order eccentricities from the reduced cross section from fire will be included in this fire design. So again, we can save this previous design in the app and go back on the project level just to set and select the fire design. So if we go on the project part, we'll just go add calculator and select CLT wall fire. So we'll quickly select the same inputs as we have on the ambient design. So we'll take 5 layers, 130 millimeters as a panel. Will for charring methods, there is a way that we can switch between the Austrian National Annex or New Eurocode method, or even standard fire test. So in this case, we'll go straight to New Eurocode design method. We'll input 60 millimeters, 60 minutes of fire resisting time. We'll have charring rates calculated according to Eurocode. Well, there is also ability to go directly with manual inputs as well. And we'll also try to see how different type of protection impacts this design. So here, let's select Eurocode. Size exposure, we can keep to the left. And if we go without protection, we can see if this is something we can see that straight away that slenderness ratio is failing. So in this case, we can try with the protection as predicted in the input design. So we'll go with the protected part. We'll have gypsum board. So twice 50 millimeters gypsum plasterboard is something that we're hoping that will be fine in this case. So I think that's according to what we anticipated. Also related some of the inputs here. So we have option with the glue line integrity option. So this is something we pointed out more in the previous webinar. We talked about fire design and how some of the inputs, especially for the new Eurocode, impacts the design, and how some of the improvements with the new code are helping or addressing some of the issues for the CLT fire design. So besides that, there's also inputs regarding the gap factor. So depending on sizes of the gap, that can also have a big impact on the design. Related to what we have for our design, so we'll quickly just go with adding the same input. So we have a Swedish National Annex. For the analysis part, again, we'll type in the same input. So no restraints, 4 meters, platform type. For the loads, we'll input the same inputs as we have on the previous part. So we'll try to add, so here we have between 2 and 3 kilonewtons. Self-weight are considered. We'll have 27, 17, 0 and 4, and we'll have out of plane 1 kilonewton. So for the eccentricity from data, we'll again use the Eurocode 5 method, and for the design code, we'll leave these inputs as we have. So we'll go back quickly, and if we change some of these inputs, see if we can optimize the design. So we have some lagging with the imagery still, but let's try see if designing with different panels can affect this design. So we have 130 millimeters. In this case, if we just reduce the gap to 2 millimeters, we can see that the design is affecting to a slenderness ratio to be below 100%. So just again pointing out some of these inputs can significantly have impacts on design. So in this case, for a 2 gypsum board, 50 millimeters, we can see that for the fire design, in our case, we can maintain the same panel, but for some situations where we want to have exposed face, this definitely will need to panel to be increased significantly. So that being said, we can quickly save this and go back to our presentation part. So as I pointed out already, so we talked about the fire design of table buildings in the previous episode. So you can find all these information and also previous webinars available on our community forum that we post after each webinar. So concerning the fire design, so as I mentioned, 130 millimeter panel we can keep it with the protection of 2 times plasterboard of 50 millimeters, as mentioned. And as we have information about the CLT wall, we can go now to the next part where we're going to talk about the CLT Shear Wall design. So in this example, we'll share the updated CLT Shear Wall calculator, which we released in the next 7 days. So in our example, we'll design a CLT shear wall located in the axis D. So shear forces acting on each floor of wall will be calculating using the tributary area. So the lateral tributary width of the shear wall is half of the distance from one shear wall to another. The design shear wall is represented in blue, while the tributary width is represented in red. So we have also displayed how this is being calculated. We have tributary width of 5 meters. And before we start with the design, let's take a look at the shear wall importance and available methods for the member design and their connection. So CLT was gaining popularity most due to its excellent resistance to both in-plane and out-of-plane loading, making it one of the key components in lateral load-resisting systems. And a lateral load-resisting system is designed to manage lateral forces that could arise from either wind or earthquake, and they're including shear walls, frames, wall, and roof diaphragms. Shear walls play a vital role by transferring loads from the diaphragms to the foundation or supporting system. So if we look at a shear wall design workflow, we can see that checks are divided between member and connection design. For the member design, we have verification for tensile compression strength, in-plane shearing of failure of boards along the joint, then in-plane shearing of a failure of glue surface at the intersection of joints, and shearing failure of the entire plate. For the connection design, there are hold-down checks for resisting overturning or tension forces, and angle brackets for resisting translation or lateral forces. In the strength analysis of CLT shear walls, there are a variety of methods which allow for determination of reaction forces that occurs at the support. These methods are mainly based on static equilibrium equations, and most of the methods consider that CLT panels are rigid. In the CLT toolbox shear wall calculator, we have 5 cutting-edge analytical methods that we implemented, which are derived from state-of-art reports. You can see the preview of the first 3 methods on this slide. So method 1 and 2 have a fixed length of compression zone, while method 3 and also 5 have the length of the compression zone is determined, so the compression utilization is always 100%. The method 1, 2, and 3 resist overturning by hold downs and translation by angle brackets. Concerning the method 4, it considers that compression is transferred only at the end point of the wall, so the whole wall is rotated at the end point. Also, method 4 and 5 resist overturning together by hold downs and angle brackets. So translation resistance in this case is not considered within these methods, so the real application for these 2 methods is limited. If we go back to our design example, we'll have the following lateral wind force. So we have 14 kilonewtons acting on the roof and 28 kilonewtons acting on each floor. For load combination, we'll use 1G plus 1.5 W in order to get the highest tension force in our hold downs. And in order to perform the design in our calculator, we need to determine vertical load, in-plane shear, and in-plane bending moments acting on the top of the ground floor or shear wall panel. The vertical dead load acting on each floor is 10 kilonewton per meter. The shear wall and a lateral load acting on it are represented in the picture on the right, and the represented lateral loads are factorized. So all of these loads that presented are calculated with the load combination we presented in the previous slide. We'll use the design of the most stressed shear wall panel, which is the ground floor, of course. In summary, we have a total vertical load of 40 kilonewton per meter, and in-plane shear force of 147 kilonewtons, and an in-plane bending moments of 756 kilonewton meter. For the connections, we'll use Eurotech shear angles 230 times 120 for angle brackets, and also Eurotech's hold downs, high loads for hold downs. So let's jump back to the app and see how all these inputs and methods are designed into the workflow. So as I mentioned, this calculator is something that will be available in the next week. So we're showing you something that we developed for internal use at the moment. So if we see here, we have pre-selected Sodra, 5 layers, 180 millimeters. On the right, we have dynamic image containing information about gravity, horizontal load, and in plane bending moment as well. And geometry is something in a number of connectors is represented in the imagery as well. Concerning specific inputs, we have first information about illumination data, geometric data, so we have the total height and length of the shear wall, and information about load. So these inputs are, as mentioned, factorized forces. So we have 40 kilonewtons for gravity load, as mentioned. For in-plane lateral load 147 and bending moment 756 as according to the inputs. For the design methodologies, we have Eurocode 5 together with ProHoltz method. So some of these verifications are not listed in the Eurocode, so we used some of the available design guides. Beside Eurocode, you can also check the FP innovations, but for the Europe context, our ProHoltz is more synchronized with Eurocode, of course. Design constant, so we have K-mode 0.9 as for we have the governing wind in our load combination. Gamma M will have maintained as 1.25 and cases as 1. For the in-plane shear properties, so this, since is on the review part from our side, this is stated as missing material properties, but in the app will be linked through the properties of each supplier. So in this case, we gathered these data from Sodra, so we have in-plane shear properties of these values. In case some of the properties are not available or listed per supplier, that is something that will be presented in this field. So just pointing out that characteristic part. For the wall connection, so the biggest power and flexibility for the design of these shear walls is listed in this section. So here, first, we can select different methods. So as I stated, we have 5 different methods. All 5 are listed in this case. So for our example, we can go with the third method that is developed by Tomasi. And for concerning that method, all the result part and information will be listed in the connection modeling, which we'll show you in a couple of seconds. For the other inputs, we also have our ability for selecting what is the edge distance of the shear wall. So we placed it at 0.1 meter from the end. We also have the connection provision, so there's ability that we can put connectors on both on one side or on one side. So in this case, we can go just from one side. And then we have information about the number of connectors. So this is related to the angle brackets. Also, lateral deformation limit, and then we have ability for inputting the properties for the connectors. So in this stage, we still have inputs for both strength and stiffness properties of the connectors. But after this, I'll also show you the newly developed shear bracket module, so where we can read these inputs, and practically in this state, this is a bit iterative process where you will have an additional tab opened for the capacities of these brackets, and then you need to fill it here, fill out. But in the next updates, we'll also already working on linking and wiring the properties of each bracket into this calculator. So in the next updates, there will be options for selecting exact products in this stage within this calculator. At the moment, so we entered 357 for the hold-on capacity. That's actually capacity of not just one hold-on, but 3 hold-downs defined by Eurotech, and also angle bracket capacity. This is the capacity of the single angle bracket multiplied by 7. We'll have the total lateral resistance. Also, the hold-down stiffness and the stiffness of the wall ceiling joint is something that we can configure, as well as tangent wall strip width. So going further, we have the output summary. So here there is a preview firstly of the connection capacity. So both for the hold-downs and angle brackets, what is the utilization. For the member capacity, checks for the tension, compression, and shear. So as we can notice, the compression is locked on the 100%. So as I mentioned at the beginning, for this third method that we used, the general compression area is determined as fully utilized at 100%. Lateral deformation checks and buckling are also performed in this calculator. So if we go quickly through some of the results, we have information on the panels and then on the connection modeling. So here, based on this third method, we have information about what is the actual both tension, compression, and shear force acting on this shear wall, or how forces are being transferred from the member or the panel through the connectors. So you can find the step-by-step method. All the information about these parts are listed in this tabulated format, as well as the references. And if we go to the connector capacity, so based on the capacities that we input and the tension or shear forces that are determined by the previous method on the previous tab, we have the utilization according to that. Going further, we have also the member design capacity. So here are performed verification for the tensile strength, compressive strength, and also in-plane shear properties. So according to, in this case, ProHolds, we have three mechanism types. First, containing shearing off failure of boards along the joint, shearing failure of glue surface of intersection of joints, and the last one, shearing failure of entire plate. So as I mentioned on some of the slides before, this is also some of the parts where you can find detailed information about these checks with instructions directly from the ProHolds guide. Next tab include lateral deformation, so including the bending deformation of the wall, shear deformation of the wall, and also overall deformation with the overall stiffness of the shear wall. And last part is in this method. Some of methods include, some methods are not including buckling, but in this case we also have information about buckling, which can be important. And the last tab is also only containing some of the references, because these calculator, as I mentioned, is developed based on some of the mostly on the research papers and some of the experimental information. So briefly about how this calculator is operating and what is the design workflow. I'll take you back quickly to the next slide, and also I'll point out on the bracket design. So, and as we mentioned at the beginning, bracket design calculator is something that we recently developed. So at this stage, you can design products from Eurotech and Siga, but more of the suppliers are coming on board as well on this calculator. So for this case, in this example, we'll check Eurotech shear angle and hold downs. So let's go to the app so I can show you on how this calculator is working. So if we go to the calculator part, and in the connection menu, you'll find below steel connectors. Selecting steel calculators, you will see the bracket design is available. So we can go into the add to the existing project. I'll select webinar 5. So I'll try to add to the same project, and here I'll open this calculator. So project ID. So let's add to the exact project, and this should be redirected to the calculator. Okay, so just give us a second. Okay, so now we're in. So for this bracket module, the overall idea is to get the information and about the capacities for all the connectors, and also depending on the different scenarios, you can design actual connection based on the different code, also the different density data, and some of the specific fastening option for all of these connectors. So in this case, I can use the characteristic density for the solder panels. For the connector data, I can select the Eurotech. And first, I can check what are the capacities for the hold down. So here, when select the hold down category, you can also check what are the exact categories, or what are the applications within each of category with the drop down menu. Here, we can select the hold down, high load. We also have the exact imageries with the preview of the design and force that is acting. And what is more important, we have option depending on the different fixing types. So depending on the each product, there is a selection of exact fastening option as well as the number of fasteners. So here we'll try to get the highest capacity. So we'll go with anchor nails for 560 and with 81 number of them. We have option for inputting the loading data, but in this case, we'll just skip that part and just try to get what is the maximum capacity of these fasteners. So we'll go the service classes. We'll have the short-term action for the load duration. Gamma is 1.3. Pre-drilling hole will set to no, and we also have the gamma M2 on 125. So here we have information about the hold-on design and also the stiffness. If we go on the second tab, we have information about characteristic loads for both tension on this bracket, and also what is the capacity of the connection. So here, if we go on the detail part, we can see how the density is being designed with this calculation. But more importantly, here, if we scroll down, here we have the capacity of the connector, and we can see here what is the actual design capacity of this connector. So we have 190 kilonewtons for this connector. If we got 3 connectors, that's something that we inputted as accordingly to our shear wall calculator as 357 kilonewtons. Similarly to this, we have option for checking other products. So let's go with the angle brackets. We can select shear angle 230 by 120. We can also see what is the geometry of this, and also what is the preview of calculator. There is ability that in this case we can also switch between these different fixing option and also pattern type. So in some cases there is ability that we can optimize the use of the connectors. In this case, we can use the same inputs, just go straight to the bracket design and see what is the shear practically capacity. So we have here information about the tension, but also the lateral capacity. So here the design capacity is almost 35 kilonewtons or 34.78. So that's also something that we use, and we know for our shear wall we need total 7 connectors of this type. So going back to our presentation part, we'll talk about the junctions between CLT floor and CLT walls, and also about the CLT compression perpendicular to grain checks. So as these type of junctions are in this particular building is something that is happening on a lot of places. It's important for every design and for every project these checks are being performed, because in some cases they can be governing, especially with some of the bigger spans, higher, more floors, and just with the thinner plates. So in our case, we'll have the governing load combination, and we have information about the total factorized line load. So we have 51.58 kilonewtons. We have K mode of 0.9, and we'll check practically this verification in axis 5. So we'll have the CLT floors of L5 140, and have also the CLT walls that we already designed in the beginning of this webinar of 130 millimeters. So we can jump back to the app. We can go on the project level, and we can add CLT compression. So here, if we scroll down, we have timber failure, and we can have here CLT compression continuous load. So we'll just select that, and we'll start editing this calculator. So in this case, we'll have option for selecting a different panel. So let's select Sodra, and let's select 145 layers. For the load support action, so we have option for edge parallel to the grain. So let's start with this, and we have option for selecting what is the top or bottom compression dimension. So we know that we have 130 millimeters walls on top and bottom, so we'll just select that for the both inputs. For the design methods, we have option for changing between the current and the new Eurocode, so we can see how that also impacts the design. In terms of the total factorized load, so we have 51.58 kilonewton per meter. We'll use automatic design of KC90. The factor also for the service classes, we'll select 1. We can take for our load duration short term action, as we have our governing load combination, gamma m can be 1.3 and cases. So we can see the compression check is way below our utilization criteria. So here we can also see how the new Eurocode have some impacts on this. So it's even more less utilization. So we can check. We know that we are on the safe side in this case, and we don't have to worry about compression, but just having in mind that these checks are something that should be performed in all situations where we have platform type CLT framing. So as we perform this short check, we can click save and go back to our presentation part where we'll have one more design scenario. So here in this next calculation, we'll talk about CLT floor and CLT wall connection. So we'll design a connection between CLT floors and wall in axis E. We have a diaphragm reaction for the shear wall of 12 kilonewton per meter. K mode is also for the short term actions of 0.9. Well, in this case, we'll use pack screws, and we can go back to the app to show you this calculator. So this is also part of the calculation that we recently released with the previous release. So we can go to add calculator and select CLT floor to wall. And we can create this connection straight away. So in this case, we can start from selecting the design input. So again, there is an option for all the calculations in the connection part to choose between the current and the new Eurocode. We have option for selecting the right support. In this case, we can go with the right hand support as is predefined. For the member, so we can select the Sodra panels, 140 for the CLT floors. And for member 2 or CLT wall, we can select 130. So this is something as we have in inputs. We can change the dynamic view from top view, section A and section B. So we have that option as well. And also we can change from discrete and continuous. So if we stay with the continuous part, we'll just have simple 1 meter strip design here. So we can go with that. For the screw part, we'll select the spec screws as we mentioned. So we can select Virex for partially threaded screws. So if you're designing some of the connection, not particularly sure in all the products from each of suppliers, you can always use the educational part where we have listed all the information about all screw types, also information about screw family, thread type, head type, diameter, length, service classes, and specification. So you can always find the alternative and the best option for your design. So in this case, we can select something appropriate for this connection. So let's go with the Specs Virex, as I mentioned, partially threaded screws, and I'll select 6 times 220, 250. So for analytical methods, we can go with Specs ETA. So all the specifics from each supplier are included in their ETAs, including rope effect calculations and edge distances, and also special specifics to each supplier, including the tip types and some other provisions. So in this case, we can maintain vertical orientation for the spacing of the screws. We can go try with 150, and we'll have flushed with member face. In terms of the loads, we'll have only the loads in the direction of the connection. So we'll have 12 kN per meter, as mentioned, and for the last inputs in this section, we'll just overview what we have here. So gamma 1.3, we'll have the short term for the load duration. Service classes can be 1, and for pre-drilling, we'll set to no. So we'll try to see how this easier part is working. So we can see that these screws are on way over 100%, so we can reduce the spacing and see if we can have 120 millimeters in this case, and see if this is something that is appropriate. So in this case, we have designed for 98.6%. Also, what would be interesting, just playing around with some of the options here. So if we go with new Eurocode, see how this also impacts the shear capacity. So in this case, this is way over what we anticipated, but just in case that in some parts new Eurocode can be interesting for the design. That's also something that it can be considered for the design. So that being said, we can go back to our presentation part. So if we keep with the ETAs and the new Eurocode, in the current Eurocode, we can see all the capacities are satisfied. We'll just click save and go back to the presentation part. So as we are practically at the very end of our presentation, I'll just use this last couple of minutes before handing to Adam and for addressing any of your questions to give you a quick overview of a new calculator that is also going to be released together with the shear wall update. So we're introducing a CLT floor penetration calculation. So just a brief information about how this looks. So here, just an overview of what are the possibilities in this. So this calculator will be developed based on the grillage method. So we have the substitute beams that will allow you to practically have an accurate overview of the designing CLT floors with a bigger opening. So together with the panel geometry, opening geometry, design methodology, so it will be fully flexible and incorporated with National Annex in all load combinations, considering some of the analysis part, deflection part, but also in terms of the results, including checks for geometry, deflection, ambient shear, and bending. What's more interesting, if we go specifically into the results, you can see actually verification of each substitute beam here. So we have option for seeing how the loads are transferred from the grillage method and how some of these calculations are being performed in the back. So this is in the last stages of developing, and it will be available for use in the next week or so. So again, thanks for for your time. I'll stop now sharing and go over back to Adam, so if we can address any questions and comments in this last couple.
Thank you so much, Marko. Excellent webinar, mate. Well done. That was awesome. So we've got some good questions here. So thank you for those who've asked, and feel free to drop any in the chat here or in the Q&A section. So firstly, Samir Manik, he's asked, could you recap the 5 methods for the methodologies of bottom connections? Do we have to pick which method we want to adopt, or can the software consider all 5 and get worst case solution? / follow-up question, what tends to be the critical failure mechanisms? Is it usually governed by connections?
So these are both great questions. Thanks, Samir. So the software at the moment cannot provide you the overview of all 5 methods. So it's up to user to select one of these methods. What we provided and what we tend to give in all calculations is flexibilities and educational part of it, all of these methods. So as I mentioned, first 3 methods consider both considers hold downs for the overturning resistance and the shear brackets for the lateral resistance. The 4th and 5th method had some are more theoretically applicable, because they both considers both angle brackets and hold downs for only or resisting overturning. So in realistic situation, I would recommend to focus on the first 3 methods, and in that case, all of these three methods, I think, will provide some similar results. So it's just what is something that user feel the most sensible in terms of the results, and experimenting what would be the right pathway to go further. In terms of what would be the critical mechanism, in most cases, it will be governed by connections, because as you notice in our example, we have to use 3 hold downs for just one for this shear wall in our example. So depending, of course, on the dimension of the shear wall, or on the type of loads and the intensity, is something that can be vary from situation and scenario to scenario. But in most cases, I think this whole workflow is designed as bit iterative between the connection and the member design. The member design is something that you can straight away check in the shear wall design. So, and the main focus is on the connection, including both strength and stiffness. So, hope I gave some clarity in this, but in the future we'll tend to provide more educational content and information about workflow, especially when linking bracket calculator within the shear wall.
Yeah. Awesome, Marko. We also had a question, are you integrating more bracket suppliers? That's one, but also how would you handle multi-level shear walls or multiple shear walls connected?
Yeah, thanks, Adam. So yes, we are integrated other suppliers into the bracket design. So that's something that as we roll up all the new updates will pop up, and will have even more value to our existing calculations. Concerning the multi-floor level shear walls, so at the moment, user can define and focus on the single shear wall, but as we show with the workflow how with the multi-stories can be used with the current workflow, we are also working on the next updates where there will be ability for inputting the whole shear walls, just applying forces to each level, and having even more clarity and more options with the designing, not just one, but the whole shear wall series.
Well said, Marko. And we've got a final question here, which I might just address at the higher level, but can we check CLT floor to beam? And we do have that calculator on the platform. We may have run out of time today to go through that in detail, but we did do a webinar, lateral stability of a post and beam in connection design in the community forum. So feel free to go into that, and you'll see the webinar end to end as well. And Sergey, thank you very much for your friendly comments there. We really appreciate that. So thank you everyone for joining us today. So we will wrap up the meeting, the webinar there. If you want to get access to the app, we do have a free version right now, which is quite advanced with a lot of great free tooling available to get you a long way of the way for, say, preliminary design of a building. If you want a pro trial, if you want access to the pro calculators, reach out to one of our partners as well, who've through our agreements can pass on free pro trials. So with that said, thank you again, everyone. We've got more questions coming in here, but yeah, feel free to send us an email or a contact us form through the app. And everyone, have a really great day, and we'll see you at the next webinar.
Thank you, everyone. Have a great day.